Good morning, everyone. I'm Joshua Weitz, professor in the School of Biological Sciences here at Georgia Tech. Nice to see many of you from yesterday. And today's QBIOS hands-on workshop will continue. I will get things going before we move into the individualized sessions with an overview, really linking some of the principles that Professor Kobe introduced yesterday morning and that you began to work on through the laboratories with the program for the day, which bridges really into additional complexities, including stochasticity, heterogeneity, and the ways in which networks ultimately modify the dynamics of epidemics, including COVID-19. So let me get us started here. Hopefully someone can let me know that they see my screen.
Yes, we see it.
Wonderful. Okay. So what I will try to do in this next hour or so is give more of an introductory lecture towards stochastic models of epidemics, and then following this, you'll begin to do this on your own, taking lessons that you learned in yesterday's laboratories, hands-on laboratories, on deterministic models of epidemics, and taking that next step. And let me just refresh everyone as people get started here in the day. I know we're working on multiple time zones, so for those of you on the East Coast or West Coast, quite early in Europe and Africa, we have folks joining us a little bit later in the day. The central objective here is really to help you integrate computational models of living systems into your research and your coursework. Obviously, we're focusing here on epidemics, and we started yesterday with an inspiring talk by Professor Kobe on what we did right, wrong, and what's next for COVID-19. And then in the afternoon, you actually begin to build these core deterministic models, the things that are really at the core of some of this cutting edge work, trying to link models with projections, forecasting, scenarios, and mitigation. And then today, you're going to take this a step further and extend those models into a stochastic framework, and hopefully this afternoon, see how you can take these models and really think of them as forms of interactive communication, and more broadly speaking, with a concluding plenary by Sam Scarpino, learn more about ways in which network science and network science theory also has been influential in understanding the spread of this disease. So what's going to happen today? We're on day 2 of this 2-day workshop, and just to make sure you understand what's going to happen next, I'm going to give this lecture, Bridging the Gap Between Deterministic and Stochastic Models. There'll be a short break. Then you'll move from this public link where we have this event style open to all into your individualized breakout rooms where, again, our team of QBIOS and guest instructors will guide these hands-on activities. And today we're focusing on stochastic models of epidemics. As a reminder, every group is working in one language, either MATLAB, Python, or R. And again, to reinforce that we've provided student versions of these PDFs so you can read, think, enter in what you think are the right answers, probably make some purposeful errors, and rest assured that we will give you all of the instructor versions, in other words, those with the answers in each one of these languages later today. And after lunch, there will be an introduction to dashboards, how you use models as a form of communication, these interactive dashboards, and this will be led by folks from the Applied Bioinformatics Laboratory, and finally a concluding plenary by Sam Scarpino. Okay, so today I'll be trying to talk about 3 things. One is to go over some of these basics of epidemic modeling, and by the end really give you a summary of what I hope each one of you was able to accomplish yesterday in your workout, in the breakout groups where you're doing your hands-on modeling. And then I'll begin to introduce some new concepts that provide a gateway to the hands-on components today, focusing on variability and epidemics, really core concepts underlying stochasticity in the spread of infectious disease. Okay, so as you probably already understood before you came to this workshop, that modeling depends on space in all sorts of ways, but we can represent interactions in an epidemic context whether through a non-spatial or a discrete or even continuous spatial representations. And here in this non-spatial representation, we've divided up individuals based on their status. We could do that in little pockets, whether it's by county or by state, or really think of this as continuously distributed across a particular region. And when we make these choices, we're also making choices about the modeling framework that we're probably going to use to represent the spread of this infectious disease. And when we do that, it's clear that we get more realistic as we add increasing notions of discrete space or continuous space, and different kinds of models are useful. And these may even fit the data better, but they're often harder to parameterize and analyze. And we often begin, therefore, our process by focusing on these non-spatial models, these ordinary differential equations. And so to refresh and remind what Professor Kobe introduced yesterday, the core workhorse of this field are these compartmental models in which we think of individuals as divided up into different states, here susceptible, infectious, and recovered. And this is true even when we're thinking about network models or individual-based models. It's just the interaction sets are a bit different. Depending on who interacts with whom will depend on proximity or interactions and so on. In this model, we think of infectious individuals coming in contact with susceptible individuals, leading to a new infection with some rate beta. And there's a typical recovery period here, Ti, from which an infectious individual becomes recovered. And we've obviously already provided to you the equations that correspond to this representation. But I think the question often arises, particularly given the mixed nature of this hands-on workshop, from the biological side, where do these equations come from? How do we take these processes and turn them into a mathematical model? My experience has been in teaching these kinds of models and others like them, is that from the biology perspective, we often think of updates, that we have a system now, some S of t, I of t, R of t, in other words, however many susceptible, infectious, and recovered individuals there are right now, and then there's the next time. And the next time is always, for whatever reason, +1, that next moment. And so I think you can see already that we could imagine a construction of an equation in which at the next time, the current number of susceptibles is the next number of susceptibles is the current minus something. The next number of infected is the current plus something and minus something, right? Where that plus is new infections, the minus is recoveries. And the accumulation of recovered individuals is essentially the aggregate addition of all these recovery events. Right? So that's a start. And we have to specifically name them. Again, these minuses and pluses correspond to the new infections, which reduce or deplete susceptibles, increase the number of infectious individuals, and recovery depletes the number of infectious individuals, increases the number of recovered individuals. So, okay, that's getting a little closer, but we still have to make choices. So how do we go about turning these words, infections and recovery, into equations? Now, to do that, you can imagine, let's focus first of all on recovery, that clearly the net number of recovered individuals that might happen between now and the next time depends on the number of infectious cases. And there's going to be some rate here that is going to control this, but ultimately, if there's no one who's infected, there's not going to be any recoveries. So we can already posit that this may just be simply a line proportional to the number of infectious individuals. And that's what we write, where we can imagine that there's some rate, gamma, multiplied by the number of infectious individuals, where gamma is 1 over the typical infectious period, and we think of this as some recovery. Okay, so we've established how it could be plausible to just simply multiply the infectious individuals by this constant and get this recovery rate at the population level. But what about the new infections? Here we have to be a little bit more cautious because this depends both on susceptible and infectious individuals. If there are neither of either category, we're not going to have new infections because we require interactions between infectious individuals and susceptible individuals. And clearly, when both are high, the total infection rate should be high. When both are low, the total rate should be very low. And if one is absent, the answer should be 0. So the simplest way to go about this is to imagine interactions at a certain number of interactions per unit time. An infectious individual may have a certain number of contacts. Of these, a certain fraction are with a susceptible individual. A fraction of those lead to an infection, and we end up getting this aggregate term, this proportionality, beta times S times I. And as susceptibles go down, likewise, the exact number of infecteds go up. And so we begin to construct what appears to be the basis for the SIR model. But of course, time is not just 1, 2, 3, 4. It's not just an interval. We can think of really any smaller interval of time. So instead of thinking about +1, we often think about plus a small interval, what we call dt. So the state of the system at the next time interval is equal to the current state plus or minus these changes, where we can think now of these beta Si or gamma I as the rate of infections per unit time and the recoveries per unit time. And if we multiply by the time interval, we'll get a total magnitude of change. What you can then also see is we can move some of those items from the right-hand side over, dividing by dt, and we end up getting things that I hope most of you will recognize as derivatives. And if we just take the next step, we recover what Professor Kobe used yesterday, which you'll often see, which sits at the core of more complex models, which is a nonlinear set of coupled ordinary differential equations in which the change of susceptibles is proportional to the product of susceptibles infected, and the infectious individuals, that change is the difference between new infections and recovery, and again, the recovered individuals increase proportional to the recovery rate. So that is the SIR model, and how we go from this image into these sets of equations. Once we have that core model in place, we can begin to ask questions of it, okay? And try to understand principles of outbreaks through the lens of what I will describe today: strength, speed, and size. Okay, to put things into context for SARS-CoV-2, and this is going back more than a year, at the very outset of the pandemic, there were questions about two key numbers. One of which is what I will term the strength, this basic reproductive number R naught, and I will go through and explain yet again what that means, which is the average number of new infections caused by a single infectious individual in an otherwise susceptible population. And at the outset, we can certainly make that assumption that the vast majority, if not all of us, were immunologically naive. So that is one way of giving an indication of how bad things might be. And the challenge, of course, is that's indirectly measured. That's the strength of the disease at the individual scale. And the other thing that obviously was concerning was this fatality rate, meaning what fraction of individuals who get infected ultimately might die. And there was significant uncertainty there. And although the fatality rate was directly measured in terms of cases, the infection fatality rate was not directly measured because many of the cases were themselves not ascertained. And so one of the challenges here at the very beginning is how certain should we be about this strength? Because this number R naught is going to tell us, in essence, how many people might be infected. And obviously the fatality rate will tell us a lot about the severity. And it's this combination, right? This combination that was so troubling and worrisome from the outset. It seemed to be a disease that had a strong potential to spread, and with a high enough fatality rate that could really make population scale impacts. And obviously, unfortunately, that has been the case. So let me now reveal why R naught is not the only number we should be thinking about, although it's often treated as such in media and in kind of popular descriptions of the pandemic. Here's a synthetic outbreak that I've constructed in advance, in which the total number of infected individuals here, or excuse me, the incidence here, I of t, is going up what's seemingly exponentially. And here we have the R naught value that I've constructed is 1.5, and excuse me, this is actually the total number of infectious individuals. So the prevalence here, I of t, and you can see that it goes up exponentially, and I've constructed it such that the basic reproduction number is greater than 1, which I think you understand leads to an outbreak. Here's another example where R naught is 2, and a third example where R naught is 2.5. And I think you should probably realize that these all look exactly the same. And I can assure you that I can multiply, so I've constructed these examples such that R naught really is 1.52 and 2.5, but at least at this time scale, they seem exactly the same. What's different is the long-term trajectory. Here I've gone beyond, in this synthetic example, 150 days out to nearly 1,000, if not more than 1,000 days, showing that these three trajectories end up diverging, and the trajectory with the lower strength, R naught of 1.5, peaks earlier at a lower level in terms of this population and ends earlier. And as the strength goes up, so too does the final size and duration of the epidemic. And here I should note this is on a log scale, so these really are quite different kind of outcomes. What is remarkable here is that these very different strength epidemics appear to be indistinguishable at the outset. And this is one of the most important things that I think you can take away when you're trying to think about epidemics, is that there's something that we can measure, the speed, right, which is the exponential growth rate of cases. And you can see here that will be the same in theory for all of these very different epidemics, even if the fundamental strength differs, and it's really the strength that's going to determine, in theory, the size, which is the peak of this epidemic and also how many individuals may be infected before the epidemic disappears. So I want to make sure that we distinguish what we can observe, the speed, what we'd like to infer, the strength, and we want to infer this because it relates to the size. And the tentative conclusion here is that many values of R0 can be compatible with the same observed rate of increase in cases, even if the projected outbreak sizes are quite different. So let's go back and see if we can unpack this. Here again is this SIR model, which I've already introduced and explained where we get these equations from in terms of this transmission rate beta and a recovery period Ti. And again, to remind everyone, there's the different population classes, S, I, and R. And again, we have these two mechanisms, infection and recovery. Okay, so let's then focus at the outset. If we start with the SIR model, and we then assume that near the beginning, the population is almost entirely susceptible. In other words, this value of S is basically 1. And sorry if that 1 looks like an I, that's supposed to be a 1. Then the change in the number of infected individuals with respect to time will simply be I, the current number of infectious individuals, times some constant. And this constant will be the difference between the transmission rate and the recovery rate. And I don't think I need to derive the answer here, but the answer is exponential. This will either grow or decline exponentially based on whether the sign of beta minus gamma is greater than or less than 0 respectively. So when the transmission rate is greater than the recovery rate, we'll get exponential growth. And when the transmission rate is less than the recovery rate, we'll get exponential decay. Right? You can then pull out the recovery rate, and you end up seeing that the sign of this exponential rate value is going to correspond to the difference between a ratio, beta over gamma, which is a dimensionless number, the ratio of these two rates, relative to 1. And this ratio is, in fact, R0. Because recall again that R0 is the average number of new infections caused by a single infectious individual in an otherwise susceptible population. A single infectious individual will be infectious for a period 1 over gamma. So that's the time, multiplied by the transition rate, tells you exactly the number of average infections we expect. And if the average number of infections is greater than 1, that one individual leads to more than one case on average, and so on and so forth, and we get an exponential growth. So if we rewrite this now in terms of, again, the change with respect to time, here I've used a dot denoting a derivative, is proportional to I, so we're going to expect exponential growth or decay with a time scale set by the recovery period, and this sign, whether or not it grows or decays, is set by the difference between R0 and 1. And you can see these outcomes here on the right, where very clearly the R0 is the infections per time times the infectious period, and we end up seeing this exponential growth when R0 is greater than 1, and decay when R0 is less than 1. The challenge has been for SARS-CoV-2, and let me just move back for a second, that we may be able to measure this value, this case increase rate, but we want to figure out the value of R0. The issue was for SARS-CoV-2, we weren't quite sure what the average infectious period was. And in fact, for more complicated models, we weren't quite sure what the generation interval distribution is. And for a very simple SIR model, this is an exponential distribution. For an SEIR-like model, it's more like gamma. And in general, we're not always sure how to characterize it. It has a mean and a variance and other characteristics. And for SARS-CoV-2, there are even other complications. There may be differences between the generation interval, that time between when someone is infected and when they infect someone else, and whether that's going to have a different mode for asymptomatic or symptomatic cases can end up playing a big role. So at the beginning, when people essentially were using more or less the same data sets to try to estimate R0, what we realized is that there was quite a large variation in these inferred basic reproductive numbers, using different kind of model choices. Branching processes, SEIR-like models, which are like SIR, but with an asymptomatic or an exposed class, and also things just like taking exponential growth models and doing the sort of projections I just did. But what people had been doing was using different latent assumptions. In other words, they took the same observed case increase rate, but made different assumptions about characteristics of the time between when someone's infected and when they infect others, and those assumptions matter. The idea is that the speed, the thing we can observe, and the strength, the thing we'd like to infer because we want to know something about size, are linked, and they're linked by the generation interval. If you'd like to read more about this, we wrote about this very early with applications to SARS-CoV-2 in the Journal of Royal Society interface. So feel free to delve into that for more. But I think one way to try to pose this is imagine that you were faced with an epidemic in which you observed the case growth rate to be about 1 month in terms of essentially an exponential growth rate. But there are two different diseases, so it's the same outcome in terms of cases, but in one case, the average period of recovery is about 1 week, and in the second case, the average period of recovery is about 4 weeks, or the period of infectiousness is about 4 weeks. Which disease has the higher R naught? Again, same outcome in terms of cases, but for the first disease, the infectious period is about a week, and the second disease, the infectious period is about 4 weeks. Now, I can't do a poll using Blue Jeans event. If you feel like putting an answer here, I'll just pause for a second. I can't even see what it says. Maybe Jessica or Audra can let me know. But ask yourself, which one of these has the higher R naught? Disease 1 or disease 2? So feel free just to take a moment, ponder, and maybe in the event chat, you can type in disease 1 or disease 2. And maybe if there's enough people who are willing to give a guess, Jessica and Audra can tell me what those guesses are, more or less.
I created a poll if anyone wants to answer with that.
Or a poll. So take a second. Again, imagine that you're facing this emerging infectious disease. There's some growth rate, which seems to be cases doubling approximately over about a month period. And we learned then later in one case, the infectious period was about a week, and the other one was about 4 weeks. Which disease has the higher basic reproductive number, has the higher strength? I'll give this about 30 seconds for folks to try to give some thoughts. And then Audra, since I think I heard you pipe up with the poll, you can let me know if anyone answered. And I'm very comfortable waiting, in the silence for long periods of time, but I don't want to wait too long today. Audra, were there any answers?
So far, there are 34 votes. 79% say disease 2.
Disease 2. Okay. It turns out it is disease 2. And why? If we just look at algebraically and we were to convert the equation I had before, what you can see is that R naught is just 1 plus this infectious period times R. And so R naught of disease 1 is 1.25 and disease 2 is 2. And that's fine, but I don't think that's quite intuitive enough. The intuition here is that to get essentially a growth doubling, let's say, a period of time over which the cases double of about a month, disease 1, which has at the individual scale about an infectious period of a week, has 4 infectious periods to double the case count, which means at the individual level, it's not as strong, whereas disease 2 takes only 1 infectious period to double the case count, which means that disease 2 has a higher average number of secondary infections per average infectious period. But it's also interesting, and you have to be cautious here, because that doesn't necessarily, you might say, well, if someone has a month of being infectious, if we can identify them early, we might be able to control disease 2 easier than we might be able to control disease 1. And that's a very different sort of philosophical approach about strength versus speed types of interventions. But I think this does reveal the fact that there's not necessarily a unique relationship. It really depends upon this generation interval distribution, and that mediates what we observe, the speed, to what we'd like to figure out the strength. And I can show this visually here too. Here's an example of a disease taking off at exactly the same speed. Here's one with longer in essence, generation intervals and shorter generation intervals. And what you can see, when the generation intervals are shorter, we have to have more of these periods to realize the same case growth rate. Here we have fewer, which implies that the reproduction number per generation is higher. And you can read, again, more about this conceptual view and how we make this practical, even when we don't know all the details of the generation interval distribution, in a paper from 2019. And really, it was some of that work that made it a lot easier for us to go ahead and try to do these same kind of inferences when we had this early case data for COVID-19. This link also helps you sort through putatively large R0 claims, and really tries to helps you parse through headlines in the news. And you may recall, this is a little over a year ago, where there was a brief period in which the claim was that the COVID-19 disease was twice as contagious as we thought. And since I really hadn't heard of any evidence that all of a sudden it was twice as contagious, immediately when I saw this kind of headline, it occurred to me maybe they were making a different assumption about interval distributions. These are the sort of values that they inferred and are not closer to 6, whereas most of prior work had estimated this closer to 3. And when you look for a given observed growth rate, right? So here we have a particular growth rate, and you try to figure out what the R0 is. In the paper, you can see that as one assumes longer intervals, and here they're using serial intervals, and I have to caution those are different than generation intervals, which I'll explain in a moment. But as you increase the duration, of the intervals, what you get are higher values of R0. So in essence, all this really is saying that assumptions matter. And I just want to point out that serial intervals are the time between an individual symptoms appear versus the symptoms of the individual that they infected. I want to point out that the serial intervals can be negative, because maybe my symptoms never appear or take a long time to appear, but someone I infected in a pre-symptomatic or asymptomatic phase actually has symptoms before me. So serial intervals can be negative, and therefore the serial interval distribution has support even for negative numbers, whereas the generation interval has always positive, right? Because it's causal. I'm infected. When are you infected? This is also relevant in terms of figuring out the strength of new variants. And I won't go into all the details here. There's a meta-archive piece out online, and if you want to learn more about that, but the same concepts apply not only when we're thinking about the spread of SARS-CoV-2 in an otherwise naive population, but even as new variants compete against wild-type strains, that if their generation intervals are different, it ends up biasing and affecting how we interpret the strength of these variants vis-a-vis the wild-type. And we're going to post all these slides, so if you didn't catch that particular link, I'm sure Audrey or Jessica can also post it in the chat. So this has been thus far focusing in on whether or not there's a criteria for liftoff, but what happens afterwards? Well, we have some expectation from this continuous theory of this SIR model, which is cases increase exponentially. Eventually, the epidemic reaches a peak. This peak corresponds to the onset of herd immunity. But again, herd immunity does not correspond to the end of the epidemic, as Dr. Kobe already revealed yesterday. Cases decline, but not everyone gets sick. So there's still some fraction of the population who never gets infected, precisely because there's been sufficient susceptible depletion that the epidemic runs its course. And the peak and total size depend on R0, again, in theory. How do we actually unpack this? How do we figure out when this peak time is? Well, if we look back at the equations for the change in the infectious individuals with respect to time, we can look for the moment when there should be no change. And that no change corresponds to the peak of the epidemic in the absence of behavior change and other factors. And this should occur when the product of S, which is now depleted relative to 1 times this transmission rate, is equal to the recovery rate, which implies a herd immunity level for depletion of susceptibles of 1 over R0. In other words, the total infected is 1 minus 1 over R0. So we get to a point where so many people have been infected, whether they're actively infected or recovered, that there are too few individuals for a new infection to spread. Now, again, that's a mathematical answer, but let's actually think of it in terms of a graphical illustration. Here we have at the outset on the left a single infectious individual in a population in which everyone is susceptible. R0 is 3. There's going to be a certain number of interactions. Those 3 individuals on average will be infected. But later on, when in this case, 2/3 are already infected. If that same focal individual is infected, what you can see is now rather than infecting 3 new people, 2 of those people had already been infected and won't lead to a new infection. Maybe they've already been recovered. That's more likely. In fact, now only 1 new individual just at the replacement level is infected, and soon not even that will happen, and the cases will start to decline. Okay, so this is your intuition as to why there can be susceptible depletion end up leading to a peak in the infection case counts, and ultimately then the beginning of the decline. And just to give you some intuition here, why people were concerned is that the level of herd immunity associated with SARS-CoV-2 was estimated to be something about 70%, but keeping in mind that people will still get sick even at this level because that's a replacement level for infection. So far more individuals will be infected afterwards. That's called overshoot. Really, this is this level if we were to vaccinate a population that we would hope that we could stop an epidemic from lifting off in the first place. But of course, networks, mobility, behavior, and other heterogeneities matter. So it's important to keep in mind these are guidelines, but these are not exact predictions, which is why there's been a lot of concern early. Maybe this was an overestimate, and then later maybe even underestimate, keeping in mind these are highly simplified models. They're guiding the kinds of concepts that underline more detailed models of the coupling of epidemic transmission and behavior. Okay, that gives you some sense, I hope, of the concepts that underlied what you did in practice yesterday. So I realize this is a public talk. There may be some folks here who weren't participating in the small groups, but for those of you who did, you know that you started both with a paper discussion in some groups, but also just basic coding practice, and then the afternoon moved into models of deterministic dynamics. And in doing so, I hope that you actually saw on your own some of these principles in action, which is what I'm going to try to review now. So I will try to highlight 3 of the components, noting that what we've tried to do in all cases in your small groups, and because you're working in MATLAB and Python and R, I won't go through or take the time here to review each one of these different languages and their outcomes, but just to point out that one of the first things you did was to try and develop a model of an SIR outbreak, and you could have used that and extended that to have different components. And each of the languages, rather than solving those equations with pencil and paper, you can think of the process of that update rule, saying if we know the change in the population, we're leveraging built-in numerical integration packages in each one of these languages, essentially to say, here we are at a certain moment of time. If we know the change, advance forward a small increment of time, recalculate the rates, advance forward a small increment of time, and so on for all of these equations. And the reason we need to recalculate the rates is because, as I've already shown you, the recovery rate and the transmission rate vary as the state of the system varies. What you are supposed to do in the hands-on component was to recognize that this transmission rate is really a product of the number of contacts per unit time times the probability of infectious contact. And that gives you your transmission rate, noting that it's modulated by the fraction of individuals that are susceptible, and we're focusing on fractions here rather than absolute numbers. You'll deal with the absolute numbers later this morning, when you work on the stochastic components. The R0 value then becomes the ratio of this transmission rate with respect to the recovery. If you choose parameters where here beta is about twice as large as gamma, so there's a recovery rate of 0.25 days, which means an average period of infection of about 4 days, and you're getting, in essence, a new transmission event every 2 days, you can see that that gives you on average about 2 new infections per every infectious individual. And if you use that as the basis for your model, what you will see is that you start with a fully susceptible population. New infections begin to spread. We actually start to see a peak in the infectious case count, and then this declines, and what you can see is we have the substitution in the end of susceptible individuals for recovered individuals. I also want to point out this very important point here, that at the end of the epidemic, we reach a new equilibrium in which not everyone has been infected. Right? Here, approximately 20% of the population was never infected, even though R naught was greater than 1. So this says that the outbreak in these continuous models is inevitable, but it's not that each individual necessarily will be infected. And if you use different values of R naught, what you would find is that for every value of R naught greater than 1, we get an outbreak, and this fraction that has never been infected kept going down, ever downwards, as you increase the value of R naught. I also point out that you probably went over this, and I'm going to try to finish hopefully a few minutes early today to make sure to reserve time for Q&A, but that was one of the core ideas we wanted you to understand, to see this characteristic SAR-like dynamics, and this also applies to things like SEIR and other variants. The other thing that we wanted to get you to have an intuition for is the extent to which there's a relationship between the strength as R naught and the size, something that I alluded to earlier, that just because you have a certain speed of cases, that's not really ultimately what's going to determine the final size of the epidemic, at least in theory. And so what we try to do is modulate the transmission rate from something which would be about 1 to something about 10, but now assume that 80% of the population is susceptible, and the remainder of the population is recovered, and you introduce a single or very small fraction of individuals who are infected. In this case, does the disease always spread? Why not? Now, clearly, if the population were entirely susceptible, we would imagine that basically in all these cases, we'd expect spread, but you can see that the 0 of R naught denotes the fact that this is an otherwise susceptible population, and I'll use the subscript EFF for effective to denote the fact that this is a partially susceptible population. And here in the output, I've shown two ways of thinking about the answer. On the left, I've shown a phase plane version in which time is implicit, where you're looking at the susceptible fraction, all of which these simulations start here at 0.8, and the infectious fraction. And what you can see with time, these black circles denote the final time of this particular simulation, that you're going to get trajectories, and I'm going to assume here that these are almost certainly the larger values of transmission rates. The higher that is, the higher the peak of the infectious fraction will be during the epidemic, and the smaller the remainder of individuals who've never been infected. What's notable when you look here on the right is if we look at this problem in terms of R naught and ask what is the outbreak size? And now here, this is a calligraphic R, and now this just denotes the recovered individuals at the final time minus those who were initially recovered. And the outbreak size is the difference between them. And what you can see here is that when 80% of the population is infected, in other words, 4/5, we need to have the R effective to be 5/4 or greater, right? Because we need to take 5/4 times that times this 4/5 to get it to be greater than 1, right? So this beta over gamma has to exceed this ratio. So if the ratio is 0.8, we need 1.25 or more for R naught. As soon as that's the case, you can see that we get more and more of the population infected, and at the higher it gets, we approach 80%, because nearly everyone who wasn't infected at the beginning, who hadn't, been recovered, is ultimately going to become infected. And this begins to show you how quickly these outbreak sizes are expected to lead. That's a very important concept as well. The difference between R naught of 1 and 2 versus 2 and 3, once you get to 5 or 6, effectively, there's really no change. Most of the population is expected to be infected. So we have to think that the big changes are happening near this threshold of R naught of 1, or in this case, in a partially susceptible population, really 1 over that partial susceptibility fraction. So hopefully you also got to this point to see that it's not just these trajectories, but really understanding this relationship in theory between strength and size. The last thing that I want to highlight, there were some other components, but I want to make sure to reserve time to talk about stochastic dynamics as a bridge to what you're going to do today, is thinking about how an epidemic becomes endemic. And for some of you in your breakout groups, you talked about this. And obviously, we can't use all of the time in the morning session to go through and recapitulate that Levine et al. Paper that came out in Science recently. But they also address the problem of how does an epidemic, which is spreading through a population, ultimately become endemic. In other words, hanging around quasi-permanently in the population. In the simplest way to deal with such a thing is to take an SIR model and essentially, instead of having the infected individuals become recovered, have them immediately become susceptible again. In other words, you recovered from it, but you don't have immunity, and you can be infected again. And that's an extreme limit. What Levine et al. Did was say, yes, you're recovered, but again, eventually your recovery wanes, and you can be reinfected, and determining the time of waning immunity, whether or not immunity is sterilizing or not, and also if you have immunity wane, the extent to which second infections are just as bad as the first one or tend to be weaker, that determines quite a bit about whether or not ultimately this SARS-CoV-2 pandemic will become endemic and whether or not it will ultimately become a mild disease. And there's scenarios in that paper which describe ways in which an epidemic spreads and with time could actually become a mild yet endemic disease. The difference between the two of them is when, in this case, an SIR model has an R0 greater than 1. In other words, the strength exceeds 1, so we have a threshold for epidemic liftoff, which you can see as an outbreak, and eventually it'll go away. In an endemic situation, you get a permanent status of a partially infected population. So everyone, more or less, at some point will be infected, but at any one point, only a fraction of the individuals are going to be infected. And that same concept, really, where we go from SIR to SI, the outbreak contexts are exactly the same. We need this R0 greater than 1 to take off. It's the final outcome that differs. And so if you want to see a more realistic version of this for SARS-CoV-2, please refer to the materials that we posted on the website where we reference this paper by Levine, which in other words takes a slightly more elaborated version of this SI model by adding additional recovered classes and the possibility of second infection. Okay, so hopefully that provides context and additional understanding for what we went through yesterday, and now I'll try to bridge the gap for what you're going to do later this morning. There's quite a big difference in thinking about fractions of populations that are infected versus actual individuals, 1, 2, 3, not 1.2, 3, 4, some sort of intermediate number of individuals or fraction of individuals that are infected. And in doing so, we can think about different ways that there may be aerosolized or airborne infections that are happening all the time, but they're happening in some ways at a rate beta, so that the moment of infection is not continuous, but rather is expected to be drawn from probability distribution with some rate beta and therefore average time 1 over beta. And we can worry about, especially these demographic or process-like noises, they become large factors when the populations tend to be small or there are a small number of cases. And this is obviously going to be relevant, particularly when we think about events or facilities or schools, and maybe when we add them all up, it looks continuous, but ultimately we think about the spread of epidemics as really arising from these discrete interactions. And in general, this can happen in all sorts of other ways, through contact, touching surfaces, and for vector-borne diseases. So how do we go ahead and do this? In the laboratory that you'll be working on today, we can take the concepts not just for an SIR model, but for generalized model here, for example, an SEIR model, and think of them in terms of reactions. And I've written this in terms almost like chemical reaction. We take the process of infection, we think about that as a susceptible and infectious individual come together. If there is a transmission event, this will turn the susceptible individual into an exposed individual. and the infectious individual obviously is still infectious. And this will happen with some rate or probability, beta SI, and if we are looking at individual numbers, we have to do beta SI over n. And we can think of this essentially as for each infectious individual, they make a certain number of contacts. A fraction of those S over n are susceptible. A fraction of those contacts lead to new infections. And that's why we get this beta SI over n as a rate at the population scale. For those who are exposed, there's another reaction, exposed to infectious. And now we have to take the total number of individuals who are exposed, multiply by some rate of onset of infectiousness, sigma, and we get now a new reaction set. And of course, there also could be the end of infectiousness. And for diseases that have potentially fatal outcomes, we might want to divide those up in terms of the different outcomes. So you can see here that we can list multiple types of events, each of which correspond to a total rate, and we have to then try to make sense of the trajectories. The reality is that with these kind of rates, we don't expect every trajectory to look the same. We have to think about measuring the system state. And here's just one example. If we had discretized the number of infectious individuals, maybe we start with 4, then we have 3 for a while, then 4, and we kind of move around almost like a plinko. Of course, the full state includes the number of individuals in all of these classes. In SEIR model S, E, I, R, and D. For SIR, it would just be SIR. We have to think about the individual numbers in each one of these different classes. And to give you an example of how this is relevant, I'm actually going to go to invoke a different disease where I and others have done some work in this space, Ebola virus disease, and really deriving from some of the data that was coming out in the 2014-15 epidemic. I'm sure you're all familiar with this. I just want to bring this up to point out that at the outset, there were a small number of cases. Ascertainment was a bit challenging. In fact, maybe not as challenging as SARS-CoV-2 because of the severity of symptoms. The individuals are symptom-free, then there are these severe symptoms, and a very large fraction of infected individuals die. If you go and look at the total case count, this comes back from fall 2014. This is data from Caitlin Rivers looking at 3 countries that really suffered the most in terms of this epidemic. There was a lot of stochasticity at the outset. People were using these exponential SIR-like models to make projections. Obviously, these projections were meant to bring in mitigation, and they ended up being far below the total case, far below some of these early predictions. But my point I think you should already see is that there's a lot of fluctuations in these numbers. Especially at this outset, we're seeing things that don't look perfectly smooth. And there's variation, obviously, at the country level. Part of that has to do with ascertainment, but part of it is really driven by stochasticity and process noise. And what I want to then have you all think about is in terms of what a case count might look like. And this is cumulative cases. And you can see you could fit an exponential to this data, and you might get an observed value. The reality, though, is that if the true generation interval, in other words, the transmission rate and the recovery rate led to a particular kind of exponential growth, and you were to rerun the tape again synthetically, you might get a slightly different answer. And you could estimate a slightly different growth rate. And in doing so, you'd have a different interpretation of the growth rate, and because you have some idea of the generation interval, what the strength might be. And you could do this again and again and find that your answers would vary. So here there's a particular observed value that's different than, in fact, what was used in theory to drive the epidemic. If we take in synthetic data different prevalence counts, the number of infected individuals at a certain time, and here each one of these gray points are values until there are 50 presently infected individuals, and then one begins to estimate the growth of the epidemic, what one finds is that these growth rates are not always the same. And if you were to pin them all at the same point together, you can see that they diverge, and the characteristic time is about 3 weeks, but plus or minus about 4 days. And the point there is that this variation is going to ultimately limit how confident you can be about the growth rate, which ultimately is the information you're using to infer the strength, which means we shouldn't be overconfident at the beginning, particularly because of the stochasticity. So how do you do this on your own? how do you build your own stochastic outbreak model? We'll use something called the Gillespie algorithm, which you will go into in detail after the brief break beginning at 10:30 or in individualized breakout rooms. And for the simplest one, this SIR model, we can think there are really only two types of events. There can be transmission, in which we remove one susceptible and increase by one the number of infectious individuals, and recovery, in which we remove one infectious individual and increase the recovered individuals by one. The rate of this first event is beta SI, and this one is gamma I. And I'm sorry, there should have actually been divided by n here. We're going to add up these total rates. So we have the two rates. We add them up, and then we determine the exponentially distributed waiting time. And then we say which event happened. So in other words, we figure out the rates. Those are events that are happening. Let's say one is happening one every 3 days, the other one is happening one every 4 days. Yet the average time is going to be less than either 3 or 4 days because both things are happening at once. So we want to add up these rates together and then wait till the event happens, decide which event happened, and update the system state at that next time. Once we update the system state, we can recalculate the rates and just keep repeating. So each time we're only making one change in the system, either transmission or recovery, rather than making this continuous change. Okay? So just to really summarize here, this is the entirety of this Gillespie algorithm. The thing that is often puzzling is why are we waiting an exponential amount of time? Before, we just seem to continuously change this smoothly. Let's try to unpack that. Let's consider events which are occurring at some rate lambda, some probability per unit time. We want to know how long should we wait before the event occurs. So for example, if the event is happening 4 per day, right, it seems like we should wait about 6 hours. It turns out, though, that is the average time, but the most likely time is really very close to 0. And that's a property of this waiting distribution. If the rate is about 1/4 per day, we might, again, wait about 4 days on average. But just as before, we're more likely to see these early events if we look at the mode of the distribution. So let's try to unpack it. What is the probability of waiting a length time tau before the event occurs? For us to wait to time tau means nothing should have happened before times tau. So the probability that the event happens in the small interval tau to tau plus d tau is equal to the probability that nothing happened until time tau times the probability, which is lambda per unit time, times that small interval of time d tau. So here I wrote this as dt, and this really should also be dt. So lambda times a small increment of time is the probability the event happened here, and we need to also figure out what's the probability it didn't happen before. What we can do is breaking up each one of these little time increments, imagining that we have a total time tau dividing by n into n small increments. So we have a very small period of time, d tau, tau over n. We multiply by this rate lambda. That tells us the probability of an event. 1 minus that says no event happened. So we have no event happening in each one of these increments, and we have to multiply each one of these probabilities n times. As we take the limit of n to infinity, you can see this is a very small number, and we can, this is sort of a shorthand way of doing it. This can be approximated as an exponential, where the n's cancel, and we end up getting an exponential distribution, which means in total that the waiting time should be exponentially distributed with average time 1 over lambda. Okay. So if we have an SIR model in which we have two processes, infection and end of infectiousness, and here I did put the n in the right place, we're going to have a reaction where we take an S individual and an I individual, end up with 2 infectious individuals. Or we could have an event of an infectious individual and they recover. And you can see these have 2 rates, R1 and R2. You add these up, give you the total rate of events, lambda from before. You jump forward an exponential distributed amount of time, and then you choose one with probability equal to the ratio of that particular rate to the total rates. And that's it. If you keep doing that, you can end up simulating these types of epidemic systems with arbitrary complexity. It also applies in other systems, gene expression, and so on. Okay. If your code works, then your stochastic and deterministic models should converge, which I hope you find surprising and cool. Here's a population now not measured in terms of fractions, but rather total individuals. This is what the deterministic model says the outcome should be. Here's an iteration of an infectious stochastic outbreak. Keeping in mind that in the deterministic case, when R naught is greater than 1, outbreaks are inevitable. That's not true in a stochastic case. So let's even try to understand this before you do your work, keeping in mind that when you do this problem, you could try to explore this yourself. What is the chance that the disease will spread when R naught is greater than 1? In a deterministic model, we've already shown it's inevitable, but not so in a stochastic model. Recall the probability of some event is its rate divided by the total rates. And at the start, the rates, when everyone is susceptible with the exception of this one infectious individual, approximately beta for transmission, and recovery is gamma. So what is the probability of transmission of a single infectious individual that occurs before recovery? Well, it should just be beta over beta plus gamma, the ratio of the transmission rate to the sum of rates. We can then pull the gamma out and see that it should be equivalent to the ratio of beta over gamma divided by beta over gamma plus 1, which is nothing other than R naught over R naught plus 1. So when R naught is about 1, we only have a 50-50 chance that transmission will happen, and in other words, disease will spread. As R naught gets higher and higher, it approaches 1, and when R naught gets lower and lower, it approaches 0. So again, this reinforces the idea that transmission is not inevitable at the population scale, even when R naught is greater than 1 in a stochastic model. Okay. So here stochasticity plays and chance plays a role, and increasingly chance plays a role when R naught is close to 1. When R naught is near 0, it's basically inevitable it'll die out. When R naught is very high, it's basically inevitable that it'll spread. The peak role of chance is really when R naught is about. So to wrap up this morning, I think I'm more or less on time. I tried to describe transmission in terms of mechanisms and gave you some core principles relating speed, what we observe, to strength, what we like to infer, because we try to have some idea about size. And just to point out that these are not the only 3 numbers. There's other things like dispersion, connectivity, and other ways that we should think beyond just these numbers in characterizing epidemics. And finally, I've tried to give you some foreshadowing of what you're going to do at 10:30 by revealing some of the core principles of this Gillespie algorithm that you can use to simulate outbreaks, and understand that just because there's a particular set of intrinsic parameters doesn't mean that the outbreaks will look inevitably the same. And we have to be aware of this, not only in thinking in the forward sense, but trying to infer things like the strength from the speed, because the speed itself may be driven by the stochasticity, and we may therefore have limits to how confident we can be, and we need to be cautious about being overconfident. Okay, so what's going to happen next? I think we have a Q&A, keeping in mind that after this Q&A, there'll be a short break, and you'll go into your individualized breakout rooms for this stochastic modeling session. And just to remind folks that the afternoon session will all be done in this single track group in this events mode. We'll have a demo of how you actually go from epidemic models into these interactive dashboards, and a concluding plenary by Sam Scarpino. We'll also be sending out an email just to let everyone know with a survey, so we can get some feedback from you about how this is all going. You can answer it later this afternoon, either in the middle of the afternoon or after Sam's talk. And we will be distributing a prize for those who've participated. We'll say more about that later, and we'll wrap up today by 5. And remember, as you go into your individual groups, yes, you can do it, and you will be helped by our team of guest instructors, including folks from the QBIOS Fall 2020 cohort taking the lead in organizing and developing materials, and our guest instructors who are helping today. Again, thank you to Dr. Jessica Irons and Audrey Davidson for their help in organizing, and the Burroughs Welcome Fund for support. And with that, I'm happy to take some questions.
Thank you, Dr. Weitz, for the wonderful talk. Please type your question in the Q&A section so I can read it.
Great. So thank you. That was Lin Jin from our cohort who's going to be moderating today. If there are any questions, it's better to put them in the Q&A component. And I'll sit around here. I'm happy to wait here. I realize there's a lot of material. We'll be posting these slides on the website. And as we did yesterday and continuing to do today, we are recording these talks, and it'll give us a day or so to post them, but we will aim to post these and add the YouTube link as well. Okay. Lynn, I think I see one question. Maybe if you could read it out, then I'll try to address it.
Yeah, sure. And I saw this one question. Could you please discuss again the waiting time distribution?
Sure. So let's think for a moment, and I'll try to avoid invoking the slides. We have an individual who's infected in an otherwise susceptible population. This is being asked by Brent Allman. And the question is, how long do we expect to wait before there's an event? So if we in general have whatever the rate is, and this could be gene expression, turning on of a gene, or here an infection event, and we have some overall rate lambda, we need to think about a small unit of time. So let's say, for example, we have something in the order of 2 transmission events per day. If we take a very small increment of time, not just an hour or a minute or even a second, then you can see that this 2 per day becomes a very small number. It really becomes a probability of an event per unit time. When we multiply that by that very small increment of time, we're going to get a very small number that we flip a coin between 0 and 1. We're almost certainly not going to have an event in that little period. We're going to go to the next period, right? And we're going to keep doing that. And what you're going to see, that's exactly that derivation that I showed, is that when we look to wait, we're going to end up getting an exponential distribution. The exponential is peaked near 0, so the mode is 0, but the mean is 1 over the rate. So if it's 2 per day, we're going to wait about 12 hours. If it's 2 per week, right, we're going to wait about 3.5 days. So I'll make sure to post that, but the way I try to derive it is thinking, what's the probability that there's an event? Is the probability there was no event until that time, and a probability of the event in a small increment. And so I'll again post that, but that's a standard way of trying to derive that exponential distribution. And hopefully that helps to fill in some of the gaps that Brent raised. And again, we'll post that slide and the video online.
And here's another question. What are some of the drawbacks of using stochastic versus deterministic models? At what point in population size and other factors does it make sense to use one or the other?
Right, so I think that there's clearly a drawback of using a stochastic model when you're trying to use it at large scales, because if you think not just from a computational perspective, but even for some of the intuition, from the computational side it gets a bit heavy, and even for the intuition, with the deterministic model, we can figure out certain things, including final size. There's actually a nice relationship there, even though that is a bit fraught when we get into real epidemics. But we can use those much more rapidly to prototype, and especially when we add many components, it's very hard to gain intuition when you start to build the stochastic model. On the other hand, we should think about the deterministic dynamics, for those who are familiar with this notion of a master equation, as being the expected value of what ultimately is a probability distribution in this higher dimensional state space. So the advantage of the stochastic model is it really captures that variability. In terms of the population size, we can also think, let's say in a simpler sense as somewhat of a guide, that we should get not just one outcome, but a distribution. So for example, in an endemic model where although we have 2 rates, in effect we have a growth rate, and then we end up getting a constant value, we would expect some spread. Something in where probably the variance is on order of the mean. In other words, we have a coefficient of variation that's going down like 1 over mean to the 1/2, which implies that once we get many hundreds, if not thousands of individuals, then the deterministic dynamics becomes a very good representation, and we don't necessarily need to use the stochastic model. But in small events, tens to 100s, and now it depends on the question, that switching point changes, gives you some sense of a guide of when you're more or less going to get the same outcome. And you can see that today. If you choose a single infectious individual to start your outbreaks, you can see that this stochastic outcome is critical, right? Because in the deterministic model, always the same thing is going to happen, but even with an R0 of 2, it will turn out to be that only 2/3 of the time do you have an outbreak, and 1/3 of the time it will stop with that one individual. That's a very big difference, right, in terms of outcomes. But once you get to have about 10 individuals, you're almost certainly with R0 2 going to have liftoff. So you can see, depending on what question you're asking and the size, these are going to intersect. And I hope that helps give you some guide as to when one might be more useful than the other.
And here's another question about the waiting time distribution. When does the exponential waiting time distribution become not appropriate?
Okay, great. It's often the SIR model for this, which I revealed for this one waiting time for the sum of rates. Let's think about a different kind of question. I want to know, how long do I have to wait between when one individual is infected and when they infect someone else? And let me think about that not in an SIR-like model, but in an SEIR model, in which first there's an exposed period in which someone's infected, but they can't transmit, and then there's the onset of infectiousness, and they can. In that case, in order for me to infect someone else, first I have to be infected, I have to wait an exponential amount of time to become infectious, and then there's another exponential that has to happen before I can infect someone else. When I take the convolution of those two exponentials, I get something that's gamma-like, which will have a mode. So rather than the mode being at 0 and the average time being 1 over lambda, I will actually have a distribution in which there's essentially no chance that it will be instantaneously after I'm infected, and it will be peaked. Both the mode and the mean will more or less coincide. There's a generalized set of these classes. The more of these classes, so rather than, let's say, one exposed state, if I have 3 or 4 exposed states, you go from something that's exponential to something that looks like gamma, and the limit will actually be a delta function, which all the events happen at more or less the same time. And the exponential and this delta function may have the same mean, but there really are extremes. And typically, what we do is make a gamma approximation, which is flexible enough and ends up being a fairly accurate and practical way to try to move from what we observe into what we'd like to know, which is this R0, mediated by a gamma approximation.
Here's another question. Have you mathematically calculated what percentage of the population needs to be vaccinated against COVID in order to stop the pandemic? How will you do that based on the rho and other factors of transmission?
So let's talk first in general about what these SIR-like models tell us in theory about the vaccination threshold, which I introduced in an earlier slide. This herd immunity threshold in the midst of an epidemic tells us the point in which infectious cases go down. There's still overshoot. People still get infected. If one had a vaccine available and vaccinated folks in advance of the spread, then in some sense, you have to vaccinate something like 1 minus 1 over R0 number of individuals in order to stop the epidemic from spreading in the first place. So in other words, for an R0, something like 3, this is often why people have talked about 70% as being a target. Obviously, the more that you exceed that, the better off of a safety factor you'll be. Part of the reason why this has been tricky is that these models are guides, but people are not interacting with everyone at the same time. We have social networks, people are changing behavior. So it's important to keep in mind that this R0 value does depend on what people do. So in the absence of knowledge about severity and people who have symptoms are going about their business, we might have to do that. If people are taking additional steps, then maybe you could even get away with lower amounts, or because of heterogeneity, lower levels. Now that is an idealized case. Once people are already infected, then our target should still be that or above. The reality is that given what we understand about immunity, which is not perfect, and we're still trying to understand more about it, but it certainly seems to be the case that 6-8 months plus individuals who've been infected tend not to be reinfected. We're still seeing the extent to which that applies to variants. The vaccines are quite effective even against variants. So I think that now, in terms of trying to understand forecasting, we do have to take into account both vaccination status as well as prior infections to get a handle on where we think populations may be vulnerable. And one of the paradoxical things right now is that places that have done a terrific job of infection control and prevention until this point remain incredibly vulnerable in the absence of rapid, wide-scale vaccination. So places like Australia, New Zealand, Taiwan, maybe parts of China, Hong Kong, places that have done a very good job relative to other parts of the world, if they don't rapidly move and increase the scale of the vaccination, they are quite vulnerable in a way in which other places, let's say South Dakota, parts of Brazil, parts of the United States, which have seen high levels of infection, it's critical to continue to increase the scale of vaccination. But the reality is that in terms of susceptibles in the near term, and we're trying to figure out how long term that will be, that a lot of individuals have already been infected or been vaccinated. In fact, if you're interested in this question more generally, I'll just type in the chat. We've tried to make some estimates of this combined effect at a website that tries to do some real-time tracking of it. I've put it on the chat if you're interested in learning more. But ultimately, this or not depends on how many people we contact, what is the chance of an infectious contact, and therefore things like mask wearing, changes in behavior. Ultimately, that was one of the reasons why, in the absence of vaccinations, people work so hard on this social distancing and social norms like mask wearing. Those were the ways to try to reduce the spread. Vaccination, obviously, is the safe and ethical way. It removes individuals who would otherwise be susceptible, moves them into this immunized class, and therefore has a direct way of keeping not just individuals, but collectively us safer. And I think we've now reached time, so I just want to thank everyone for their questions. We're going to take a short break now for about 15 minutes and go in to the other sessions at 10:30. Oh, and then, there is one more question. Chrissy asked one more question. Let me just try to answer that one. Is that okay, Lynn? Can I try to answer one more?
Yeah, sure. And there's actually another one. There are two, I think.
Right. Yeah, those are both obviously, let me try to answer. I think they're both around this idea of variance and efficacy. So these are both trying to ask this question of how do variants influence outcomes. When we think about the variant question, I'll just refer you to the paper by Levine in some sense. But this goes back to whether or not individuals who've been infected are then susceptible to infection again over what time scale. And this is one of the ways in which SARS-CoV-2 or COVID-19 as a disease class can ultimately move from epidemic to endemic. And depending on whether or not there's really sterilizing immunity, both on the vaccines or prior infections, or whether or not individuals may show up as PCR positive, but essentially have mild disease, and we end up getting to a place where something that stops society has caused in the United States 600,000, if not more, fatalities and millions globally, becomes in essence a mild disease. And the way we'd like to get there is obviously through the safe and ethical way, which is through vaccinations. And then there will have to be monitoring of the efficacy of the vaccines. And that goes back to Roman's question, trying to understand the extent to which a vaccine prevents disease or prevents severe disease. And again, keeping in mind that these emergency use authorizations for the 3 vaccines available in the United States, the Pfizer, Moderna, and J&J, we're all focusing on severity. Because if you can stop the severe outcomes, that's really what has stopped things. It's not cases, but the fact that until this point, cases implied ultimately hospitalizations and fatalities. And so if what the vaccines can do is, as we're learning, actually are even better than we thought. They seem to reduce the risk of being infection and reduce the risk of transmission, but ultimately the way in which they were proved was through the lens of, do they reduce severe infections? The answer is yes, at very, very high rates. So obviously in the long term, this is something that those on the vaccine side are going to keep having to monitor. And obviously, to the extent to which vaccination efficacy is not 100%, that modulates the extent to which individuals, the fraction at which we're expected to immunize individuals, will have to go up. With that, I think I will put an end to the question session, but thank you very much, and thank you so much.